So today I'm going to talk about a simpler problem. I'm going to look at the map from z to w given by w equals z squared. In Cartesian coordinates, if we map vertical lines in the z plane, we get parabolas in the w plane. We get parabolas that go this way, the vertical lines. And if we map horizontal lines in the z plane, then we get parabolas that go the other way. But in fact, it's much simpler if we work in polar coordinates. So here's a polar coordinate plane. So z is r times theta, r times theta, r times e to the I theta. In this case, r is the distance from the origin, and theta is the angle from the x-axis. So if z is r e to the I theta, then w is r e to the I theta squared, and all the usual rules, of course, apply. So that gives us r squared times e to the I times 2 theta. So the graph of w in the polar coordinate plane is going to be very, very similar, because the lines r equals constant will be mapped into the lines r squared equals constant, which is a circle. So a circle in the z plane gets mapped to a circle in the w plane. So the picture looks identical, just the scale changes. So if we have r equals 2 in the z plane, then r squared would be 4, so that would be a bigger circle in the w plane. So we can actually have one graph here doing double duty. So that's circles get mapped to circles. So what about places, the rays where theta equals constant? Well, if theta is constant, then 2 theta is also constant. So a ray, theta equals constant, gets mapped to a ray, 2 theta equals constant. So the graph is exactly the same kind of graph. There's only one difference. And the difference comes not from the map theta to 2 theta, but it comes from the restriction on the range of theta. So we know that minus pi is less than theta is less than or equal to pi. And that just says that when we draw a circle here, we start at minus pi, and it doesn't quite touch the negative axis here, and it goes around in this direction, and it comes up, and it does touch on top. Okay, so that gives us one round of theta. So that means that 2 theta goes from minus 2 pi up to 2 pi. Well, this graph is getting a little crowded here, so we'll draw it again. Minus 2 pi, we back up 2 pi, is almost to the positive axis again. And so we go from minus 2 pi up to 0, and we cross 0, and we go all the way up to 2 pi. Now, if we notice, every single ray gets cut twice. Well, that makes sense, and that includes the ray here. It gets cut when theta equals 0, and cut when theta equals 2 pi. But it doesn't touch at minus 2 pi. There is an infinitesimal, if you like, gap between there. So the w plane gets touched twice for every point in the z plane. That makes sense. If we want to go backwards, we know that there's going to be 2 square roots. So this just gives a polar coordinate complete description of what's going on. In the Cartesian coordinates, it's also true that everything gets touched twice. What happens is this vertical line gets mapped to exactly the same parabola as the vertical line on the other side. So each of these parabolas gets traversed twice. It's just harder to see. Whereas here, each ray gets traversed twice once. So for example, if this is pi over 6, then pi over 3 gets hit once from pi over 6, but it also gets hit from pi over 6 plus pi. So pi over 6 plus pi gets mapped to pi over 3 plus 2 pi. So this ray also gets mapped to this one. So that's just the touching everything twice on there. But I want to point out that for pure powers, Cartesian coordinates are possible, but polar coordinates are much better. Cut.